So let's see how much time we needed to finish a test. Right? The first problem is to express an integral as a limit Riemann sums. Okay, so that just asks you to record the definition of the integral, right? So I give a function like that. Okay, so the student do not read this question carefully. They just evaluate the integral, okay, and give another use a substitution. But which I don't want it. I don't want it to give me the number. Okay, you can evaluate this integral use substitution, no problem. Okay, some you cannot, some you can. Okay, this is a continuous function by a Riemann sum. Okay, this is actually for continuous function. Okay, you can choose delta x to be 1 minus 0 over n. Okay, and you can choose a special Riemann sums, which is give me 0 plus I delta x. Okay, then the Riemann's the integral is going to be the limit as n approaches infinity, and this is f of x, so just xi squared 1 plus xi squared, and then delta x. Okay, but that's not a final version because you have to tell me there's xi, so it's better to put the xi into the expression. Okay, it's going to be I over n square. There's no square here, can enumerate, no square. Right? Then 1 plus I over n square, and this 1 over n. Okay, this is what I want. Very simple. If you know how to do it, simple. According to Riemann, by definition, this integral is going to be some limit of the Riemann sums, but the Riemann sums could be very arbitrary. The partition of the interval can be arbitrary. But also Riemann says that, well, if the function is continuous, you can take special partition. Those are special partition that equal ranks. Sub-intervals have equal ranks. Then the limit should be equal to the integral, the value integral. Okay. We learned the substitutions. So we should be able to evaluate this integral. This is a very simple integral. Okay? Unless you haven't done any exercise, I have no clue otherwise, right? So like this, it's clearly the substitution will be this. Okay, you let w to be cosine x, not sine x. Then dw is negative sine x dx. Then you put into the form integral, it's going to be w squared, sine x dx will be negative dw, right? Then you find the antiderivative of this function. Okay, so answer will be okay. Now what's if I change from a little bit, still the same function, then it's be more complicated. For example, like a cosine square is going to be 1 minus sine square. So 1 minus sine square x, sine x. So dx. So you get sine x integral, then sine cube x dx. So if I ask you to find the integral, evaluate integral sine cube x, maybe it's difficult. More difficult than this. But if you look at this identities, you know what is the integral sine x, right? Then you should be able to find integral sine cube x. Okay, sine cube x. Okay, so this is use a substitution. And here's the integral. Okay. This is a quotient of two functions. We don't have the, it's not like a derivative. This is integral. So we don't have a quotient rule for the integral. Okay, we only have the quotient rule for the derivative, the quotient of two functions. So the only way you can solve this problem is you have to express the fractions, the sum of power functions. So 5 x squared divided by square root of x will be 2 minus 1/2, 3/2. And here x to the 1/2, here's x to the negative 1/2 dx. Okay, then you can evaluate the integral. You can easily find an antiderivative of each of the functions. So it's 5, 1 over 3/2 plus 1, x to 3/2 plus 1, here's 3, 1/2 plus 1, x to the 1/2 plus 1, and plus constant. Then you simplify it. Okay. So the answer will be, this is going to be, 5 is cancelled out actually. So after you simplify, just be careful. This is going to be, it's going to be 2x to the 5/2, and that's going to be also 2x to the 3/2, right? And plus 2x to the 1/2, and the plus constant. Okay. Now, if I change the problem a little bit, think about it. This is not on this test. Okay, maybe I have to look at it. Okay, if I discuss this problem before, then maybe. But I'm not going to discuss it here. If I change it to this, can you do it or not? Okay, think about it, okay? I'm not going to tell you how to do it, but you're not able to repeat the same idea, okay? But you have to do something. So this is a question. The second one is, you are given the function x plus 1/x on the interval from -1/2 and 3. Find the absolute extreme values. Okay. Now, this is a continuous function. Okay, this is a continuous function, and so this is a continuous function. So definitely has the absolute maximum value, absolute minimum value, right? Then absolute maximum, absolute minimum value. So the question, how to find it? According to the theorem, the function has maximum value somewhere, either at critical number or at the end point. So all I have to do is just find the critical numbers, then evaluate the function at those special numbers. Then you compare which one is larger. Okay? You don't need to tell me whether the function has local maximum value or local minimum value. I don't need to know that. So you don't need to do extra work. Okay? So find the critical numbers. It's 1 minus 1/x squared. Okay? Just find the derivative. Okay? So you set this to be 0. So you get x squared equals 1. And x is going to be plus minus 1, x is only 1 positive. Because in the interval, there's only one solution. All right, so one critical number, 2 endpoints. So let's evaluate those values. 1/2 is going to be 1/2 plus 1/2. It's going to be 1/2 plus 2. It's going to be 5/2, okay? F of 1 is 1 plus 1/1. It's 2. It's a smaller number. F of 3 is 3 plus 1/3. It's 9. It's 10/3. Okay. So, anyways, this is the largest number. Which one is the smallest number? That's the smallest number. So this should be the absolute minimum value. This will be the absolute maximum value. Simple, right? The value, when we talk about value, it's value, number. All right, so now the next problem is about set up an integral. Sketch the graph and the set up integral for the volume of the solid. The solid is located by about the y-axis, first of the region. The region is enclosed by the curve y equals x squared minus 2x and y equals 0. Okay, rotation is about the y-axis. Okay, so you have to sketch the solid and then set up an integral for the volume. Okay, so please do, sketch the graph first. Okay, I'll give you minutes. Think about how to set up the integral. Are you able to set up 3 integrals? If possible. Okay. Right. You sketch the graph. Sketch the 2-dimension region first, then 3-dimension. Right? It's harder to imagine 4-dimensional high dimensions. Maybe if you have time, on YouTube, you can search how to understand 4-dimensional objects. Very interesting. Some are very interesting lectures. Especially the cube, 4-dimensional cube, how do you view it? All right, so this is a 2-dimensional region, okay? And the 2-dimensional region, if you rotate about the y-axis, that means you have to go to 3-dimensional space. Think about it, right? Then if you rotate the solid in a 4-dimensional space, then you get 4-dimensional solid. Okay, it's interesting. That's hard to imagine, right? Now you can see it, right? If you rotate about the y-axis, right, you get something like that. So this is a solid in 3-dimensional space. Okay, and so you have to add another axis. This is the y-axis. This is the x-axis. This is the z-axis. So you can imagine that if you rotate this one about the z-axis in a 4-dimensional space, that's more. It's hard to imagine how does it look. Okay. Okay. You can also, yeah. Okay. So now how do you set up an integral for the volume? You have 2 different ways to set up an integral. One is use a plane to cut the solid. It's more difficult. The reason is the cross section will be two disks, consistent between two disks. How do you determine the radius? Right? For the given y value, you have to solve for x. It's not the easy. The easiest way to do is to cut the solid. You cut the solid using cylindrical shells. What they are doing actually is going to be is just look at the level surfaces with the same distance to the y-axis. Okay, so the distance is going to be r, right? And the area of that surface is going to be AR. So the volume is the integral of AR dr. Okay, and R expand from 0 to 2, I think, because the largest possible value for R is 2. Right? So how can I express the area of that cylinder? That cylinder is 2 pi r h, so you have an h here. So if you are able to express h in terms of r, then you can solve the problem. But you can do that, right? Because if that is a point has coordinates x and y, I is going to be x, h is going to be y, but the y is related to x by x squared minus 2x. So if you don't want to use the x variable, just use the r variable, then x is expressed by r. So this is a 2 pi r squared minus 2r. Okay. So you put there 2 pi r squared minus 2r and dr. That's it. Of course, r is x, x is r, so you can also express it in this form. Okay, but it's harder to express in terms of y variable. Okay. Okay. If you have to use y variable to evaluate the to set up integral, then you have to use disks. Okay. Yeah, it's not easy to determine the radius. Okay. So let's try. Why not? Okay. Oops. Okay. All right. You can use disks to cut it. Okay. Let's try use disks to cut it. I'm going to set up. Okay. So this is 3D, right? So cut it in the form like that. Right. So this is this is a disk. Okay. So from here to here is R1. This is going to be R2. So what we try to do is actually we use a plane parallel to the XZ plane. This is a Z, this is X, this is the Y axis. We're actually trying to use a plane like that, parallel to the XZ plane. Okay, so the height here is actually the Y value, right? So you can use R here. Okay. So what you're trying to do is you have to figure out the highest point. The highest point, I think, is going to be 1. Okay, where? When x equals, hold on, let me check. Did I draw the picture correctly? This is under the x-axis. Okay, what I'm going to do here. So the graph x squared, y equals x squared minus 2x. In order to not to make any change, this is going to be, yeah, my picture is wrong. Okay, that's right. I needed to change the sign, because otherwise, you see, when x equals 1, the y value is -1. Right? So I'm modifying a little bit for the function. I'm not going to rescale the picture. I put a negative sign in front. Okay, everything is fine. Okay, then this will be negative. This will be positive. Negative, positive, negative, positive, negative, positive. Okay, this will be, then everything's fine. Okay, change the probability. All right, so the highest point here is going to be 1 and 1. When x equals 1, y is 1. So the value, the volume is going to be integral y value from 0 to 1 and a over y dy, okay? For the fixed y, what is the area of this cross-section? The area of this cross-section is going to be pi capital R squared minus pi capital 1 squared, capital R 2 squared, right? So for that fixed y, how can I find the x value, R2, R1? You just need to solve the equation, because it's going to be, right, negative x squared plus 2x. So the solution for x, for the fixed y, solution for the x, you get 2x values, okay? So let's see, x squared minus 2x plus y equals 0, and the x equals negative b plus minus b squared, so 4 minus 4ac, okay? So you get two solutions. X1 is a smaller number, and that is going to be, take a 2 out, right? So it's minus. X2 is 1 plus square 1 minus 1. So if the corresponding point on the graph will be here, x2 and the y, that is the point x1 and the y, right? So R2 is x2, R1 is x1. Okay, so now you go back. Pi 1 plus right? So that is the answer. It's complicated because you have to figure out the radius. You give the given y. So this method is called using discs. Actually, what you're doing is you use a plane to cut the solid slice. Okay, and y is the distance function between the plane and the yz xz plane. Okay, yeah. In geometry, yeah, this actually those two methods. Yeah, those two methods, they both come from one single formula. Yeah, we call it the distance, called the isoperimetric formula. Yeah, for the areas. But we're not going to go through that part. But anyway, the reason this is true because y is the distance between two planes. Okay, and the reason why cylindrical methods works just because the r here is going to be the distance, okay, to the y-axis. This is y is here. You can use r, okay, it's a distance to the y xz plane, okay. So the set could be one line like y-axis, or could be the one plane xz plane. In general, yeah, it's harder to say. In general, yeah, if you have a, put this way, if you have a You have a strict line. Yeah, the cylindrical method means you consider all the sets here they are, and there's a portion of that. Okay, this is AR. Then the volume is going to be integral of AR dr. Okay, and I is the distance to the fixed axis. Okay, and the volume of the solid. So solid could be anything. Yeah, this is the intersection part of the cylinder with the solid. Okay, the intersection part. Then, but you can also consider the distance function to the plane. Okay, so then you have a cross section here. If this is AR, then the volume is going to be AR dr. It's the same. This is a two typical formula. So you get disk. Okay, so you cut this. This is a fixed. We call the references plane. Okay, yeah. The top one is you have a one-dimensional line. So that's two ways to measure, to evaluate, to find the volume. The volume, roughly speaking, the volume is just the integral of the area of the cross section. The cross section could be flat, like in this case, fixed plane, and you have family of planes just like a CT scan. Okay, just like a CT scan. So if your body, you get a sequence of pictures from the bottom, from the seat to the head. If we have 1,000 slides, and each slide, if I know the area cross section, I can find the volume in the body. Just to integrate this. Okay, so you can also measure figure out the volume using cylindrical knife instead of flat knife. It's harder to measure, but this is the distance to the fixed axis, and then the wind slides not necessarily cylinder. Okay, could be a portion of the cylinder because if the body is not as symmetric about the axis, and when cuts one slide, then you don't get a shield. It could be only portion of the shields. Could be only part of that. Could be only part of that. Okay, it depends how does the solid look like. Here in California, what they're doing is they have a frozen dead body. That's what they did. Okay, maybe not a good idea, but they did. Cut the frozen body into 10,000 slides. 10,000 slides, very simple. And each slide they take a picture, they put together. What they're going to do, if the student attend the human anatomy courses, they don't need to touch the body. They all have to do is put the glove on the hand, and on the screen you have a 3D image of the body. Every place you can cut it, open it, you can see it, then close it. It's a software, so it's a real body, but it's software. So it's much better. Of course, later on, some people really become surgeon, doctors do surgery. Then you have to touch the body. Otherwise, you don't need. Just understand the body structure. That's the technology can provide. Okay, and mathematics is useful, very useful everywhere in medical science. I'll just give you one example. Like, how do you check whether you have a colon cancer, right? It's especially important for men over 50. How do you do that, right? The traditional way is you eat something, put something in the body, and then take pictures. That's very painful. But now the technology using geometry, okay? The fundamental paper is actually published in the Indiana Journal of Mathematics in 1954. So they use that paper, okay? They make an equipment that can get the image of the inner part, okay? Even like a brain cortical surface, you can open the brain, right? And then project the screen. So doctors, patients can all both see it. It's deformed, but they see. You can see what's wrong with that. Okay, so that's place. That is a place where you can use mathematics. Okay. So the next problem is the region enclosed by curve, enclosed by the following curve: y equals 1, y equals x squared. Okay, and this rotation is about the x-axis. Set of integral for the volume. Then you can use any method to solve this problem. I wish you to set up 2 integrals, for the exercise, because sometimes it could be, you're required to use disks to set up integral. Sometimes you are required to use cylindrical shells to set up integral. Okay, so step 1, draw the picture. Y equals x squared, like that. Y equals 1. That is right. So the region is bounded by these 2 curves. What is the region? It's not below the curve, below the parabola. That is the region above. It's between here. So it's very important what region you're talking about, because you end up with the different solutions. Okay, so that is the region. You're going to rotate about the x-axis, so you get 3-dimensional space. Okay, you get 3-dimensional space. So that you can see from all sides. It's a cylinder. Right? It is a cylinder. You can I think this cylinder, you can use a cylinder, but you can also use this slice by slice. Okay, so this is a y-axis. This is an z-axis. I'm going to use the plane parallel to the y-z plane to cut it. Okay, so the idea is get a disk. Yeah, so this is a 3D picture, right? It's harder to read it. Okay, so one slide, I want to color it. It's interesting. So the cross section has no color, but the remaining part has color. Okay, so this is so this is a distance between this plane and that and the YZ plane, right? Is going to be X, right? So that is a distance. I call it. You can use X variable, you can use R variable, doesn't matter. I equals R, and that will be AR, the area. So the volume is going to be integral of AR dr. Guys, the area of the integral of the area of cross section. But I is it's not radius. I is just this distance. Okay, between the plane you're using and the YZ plane. But I is going to be X. But for this X, okay, and there are 2 disks here for the fixed R. So we have capital R2. We also have R1, right? So A over R for that particular point is the difference of those two, right? So what is R2? I think R2 is clear. R2 is always equal to 1. The only R1, you have to be very careful, but for the fixed X, R1, yeah, R2 is a 1. R1 for the fixed X, for that X, R1 is going to be X squared, okay? So if you want to use the X variable, if you want to R, then use the R, right? Otherwise, you can use the X, okay? So this is going to be R squared, okay? So the volume is going to be integral from 0 to 1 pi 1 square minus pi X squared or R squared, it really doesn't matter. Okay. Or you can also but usually you would most just use the X variable. Okay. So use X or use Y variable, then don't use R. Okay. R is the original variable. In the okay, R represents the distance between the plane and the fixed reference plane. Okay, so that is a picture, right? Now, if you use a cylinder, do you think it's better or not? Okay, this is an x-axis, this is a y-axis. Okay, that's a picture. So I'm going to use cylinder. That means I can see the points in the solid with the same distance to the fixed axis, which is R. Okay, so if that volume, how do we? Yeah, we can draw like that. If that area is AR, so the volume is going to be integral of AR and dr. R is from 0 to 1. That's it. Again, the same formula. It's always the original formula. Doesn't matter, right? So R is the distance from the fixed axis, and you can see the surface inside the solid with the same distance to the x-axis. Therefore, that's actually cylinder portion of the cylinder. Then the surface area of the cylinder, I know how to calculate. If I know this h, then AR is going to be 2 pi RH. So if I'm able to express h in terms of R, I'm done. But how to get h? Look at this particular point. Okay, look at this point. Y is here, X is here. So R is going to be Y. But the X, well, X actually, H is going to be double of the X because it's symmetric, right? So for the fixed Y, how to find the X? You see, Y is going to be X squared. So that implies X is plus or minus square Y, right? So that means H is going to be positive Y minus negative square Y, which is 2 square Y for the fixed Y. Y is just X, R. So H is going to be that. R is Y, H is 2 square Y. So that give me this relationship. So I'm going to, okay. So I put it back. And the 4 pi R squared R d dr. Okay, you can also use Y variable, no problem. Use Y variable because I is Y, then you have this. Okay. Or doesn't matter, right? No difference. You always choose a point. Draw the graph, choose a point on the curve, original curve you use. And then And you express I and H in terms of X and Y. And because X, Y are related, so I and H are related. That's it, right? So we have two different ways to express. On the final exam, you are given the region and the rotated above y-axis or axis. You will be asked to set up two integrals for the same solid, period. That's the reason you need to understand both. You cannot just memorize a very specific formula. The only formula you need to memorize is just integral of AR dr. Right? But you have to figure out what is R, what is, yeah. You have to find out this, but you can later on you can use X variable or Y variable, that's right. Okay. Technically you can use X variable, not necessarily use Y variable here. Okay, because X is going to square Y. But it's just a little bit more complicated. All right, our next problem is a third problem. Rectangular tank with a square base and open top. Okay, square base and open top. Okay. 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 Open top. Oops. Right. So square base was open top. What is the question? This one has a volume 32 cubic units. Find the dimension that will minimize the surface area, okay, including the bottom part. Okay. So the volume is fixed, 32 cubic units. Okay. Find the dimensions that will minimize the surface area. Okay. So dimension, what is different, right? The base square. So square is base. So let's use you can use X and Y. You can all use A and H. Okay. So if you can tell me A and H, that's enough. All right. Write down the formula for the surface area. Okay, so you express the surface area in one variable only, either in A or in H. Okay, then you find the minimum value of that surface area. So first of all, you write down the volume formula. Volume is going to be A squared H, right? That's going to be 32. The surface area is going to be the base, A squared, and you have 4 identical sides, A times H, so 4 AH. And then clearly, I should solve for H in terms of A from the first equation. So it's going to be AX plus H is going to be 32 over A squared. So A is arbitrary, but H depends on A. A could be very small, very large. Then the box changes a lot, right? If A is very small, this will be very long box. Right? A is shrink, and because you want to keep the same volume, that takes more surface area, right? So here you get A plus, A plus, it's 4 times 32. I'm not going to change that, right? So clearly, if we draw the picture for the relationship, draw the graph for the relation A and the capital A, the graph looks like that. When A approaches 0, it goes to infinity. When A approaches infinity, it goes to infinity. So somewhere here has the smallest value, all right? Yeah, capital A equals little A squared plus X. So when little A approaches 0, capital A, because this approaches infinity, so that's why it goes to infinity. When A approaches infinity, this term approaches 0, but that term approaches infinity, so it goes to infinity. So both ends go up. Somewhere in the middle has a minimum value. To find it, just find the derivative, right? So dA little a is 2A minus A squared. Okay, so I'm not going to show you how to find derivative. That's you know how to do it. And that should be equal to 0. Then both sides divide multiplied by A squared. So 2A cubed equals 4 times 32. So this is going to be 2 times 32, which is 64. 64 is going to be 4 squared, right? It's going to be 4 cubed. 4 times 4, 16 times 4. Yeah. So 8 is going to be 4. So you find the dimension. If A is 4, H is going to be 32 A squared. 32 4 squared. So it's going to be 2. Yeah, so the box must be in the following form. The base is a edge length is 4. The height is just 2. So if you want to make a box for your company, just say without top, just box with bottom, right? And the wood and the square base, okay? Assume the square, that's the important condition. Then you always should make it in the following form. The height is half of the edge length. That minimizes the cost. If you only make one, it's okay. If you make thousands, right? That saves you lots of money. Okay? Because the process to make a box is the same, right? It's the same. Yeah. For the same volume, this container. So like a U-Haul, for example. How about like this? Good example. Of course, we have a cover, right? Without cover, the box like this. How do you design the square? Right? Square base, the height should be half of the edge length of the bottom. Bottom of the square. Okay. So this max for the same volume. This minimizes the surface area. the same. So here's a function x over x minus 3. Let's sketch the graph and find necessary information. Okay, so find necessary given a function like that. How do you sketch the graph? Well, first thing you have to do is to see asymptotes, intercepts, right? So intercept when x equals 0, y is 0. I know it passes through the origin. Okay, no problem. So then asymptotes. Asymptotes, x equals 3 is a vertical asymptote. When x equals 3, it's undefined, it's grew up, right? But also when x approaches infinity, y approaches 1. Right? This is going to be 1 just because the limit as x approaches plus minus infinity, it's always equal 1. And this one, because when x approaches 3, plus minus, that's the infinity. If it's plus, x minus 3 is a positive infinity, right? So that's the reason you get asymptotes. All right. How do you sketch? I don't want to find the derivative right now, but I can sketch the graph. And when x equals 1, when x equals 1, let's go. And when y equals 1, this is horizontal asymptote. Okay, so the graph is controlled by these two lines, right? And the graph passing through the origin. The graph passing through. So we put a point here. All right. Nearby infinity. Nearby infinity, the graph will approach to. So nearby the vertical asymptote. How does it look like? Nearby x equals 3, x equals 1. Okay, nearby x equals 1, y equals f of x, right? X minus 3. No, wait a minute. So x is 3, not a. I did not look at. Yes, this is the asymptote. No, still the same. Let's draw the graph a little bit far away from here. It's going to be like that. Okay, 3. Okay, this is the x-axis. This is y-axis. Nearby 3, x equals 3. Nearby x equals 3, the numerator is just 3. So this is going to be like a 3 over x minus 3. 3x over minus 3 when x greater than 3 is positive. Should be here. When x is going in that direction. When x greater than 3, getting close to 3 goes up. And this must be go down like that. Okay. So the graph looks like. Okay. So the graph passing through the origin, so it must be like that. Okay. The only question is whether it will go across the asymptote or not, horizontal asymptote or not. If not, it's always below the asymptote, right? It's always above the asymptote here. It will not go to the asymptote. I'm pretty sure it's not going to be. It's not going to be. Yeah, it will not cross this horizontal asymptote. The reason is x over x minus 3 is never be equal to 1. Okay. Why? If it's equal to 1, then 0 equals -3. Okay, so that means the graph is always above the axis, above this horizontal asymptote. On this side, is on the left-hand side, it's always below the horizontal asymptote. So we already sketched the graph. The next thing we have to answer whether the graph changes concavity somewhere. I don't think it should concave. It's always concave down. It's always concave up. No points in inflection. Okay, but you can check that, right? So this side, I'm pretty sure it's going to be f prime is going to be positive, y prime is going to be negative. Here, y double prime is going to be positive. Here, y double prime negative everywhere. Before I find the derivative, I already know the sign. Negative means it's concave down. Second derivative negative everywhere. Okay, first derivative negative means going down. Okay, decreasing. No, this should be negative. Okay, so it's going down. It's going down. Both sides are going down. Okay, but the second derivative is positive. It's concave up. Why the first derivative is negative here, negative there? On each side, it's going down. Okay, let's verify this, right? Let's verify this. Okay, the first derivative, x minus 3 squared, 1 times x minus 3 minus x times 1. Okay, so it's going to be negative 3. It's always negative. Yes. Second, I think it's going to be 6. X minus 3 negative 2. Okay, negative 3. This one depends on sign. Okay, if x is greater than 3, it's positive. If x is negative 3, negative. If x is going to be less than 3, it's negative. So if x greater than 3, negative. If x less than 3. So when x less than 3, concave down. When x greater than 3, concave up. Okay. Concave up. Concave down. So next problem is about, we're going to, let's see, let's go do a similar problem. F of x equals x squared 4 minus x squared, and sketch the graph. Okay, and just sketch the graph, find all the required information. So this is another rational function. Okay, sketch the graph. So the domain of the function is different. So the domain of the function is going to be x squared less than or equal to 4. So actually, it's going to be from negative 2 to positive 2. Okay. So that is the domain of the function. Okay, the function is only defined from negative 2 to positive 2. So let's sketch the graph. Okay, clearly when x equals 0, y 0. When the x equals plus minus 2, y is also 0, right? So the graph passing through here negative 2, here is positive 2, this is 0. So when x positive, it's positive. When x negative, it's negative. We already sketched the graph. So even, yeah. First of all, it passes 3 points. Because when x equals plus minus 2, y is 0, right? Why? Because x squared is going to be 4. When x equals 0, it's going to be 0. Then the sign of the function depends on the sign of x. So when x is positive, it is above the x-axis. If x is negative, it's below the x-axis. I think the function somewhere. From this picture, I can tell that one side concave down, the other side concave up. I just don't know where's the maximum point, where's the minimum point. So I'm pretty sure this side, the second derivative is negative, this side, second derivative is positive. And here, the second derivative is 0. This should be the inflection point where the concavity changes. So before I could do any calculation, I need to know. Okay? And if I'm able to find the two critical numbers, then I can tell where the graph is increasing, where the graph is decreasing. So the only thing I need to do here for this problem is find these 2 points. Then I need the derivatives. Okay, I need a derivative. I should get 2 symmetric numbers. Okay, so f of x equals x 4 minus x squared 1/2. It's important to know the result before you do the calculation because it's possible to make a mistake. I should be able to get 2 critical numbers, plus minus the same number, okay? So it's going to be 1 times 4 minus x squared plus x times 1/2. 4 minus x squared to the negative 1/2. Then you differentiate x squared. So you get a negative 2x. All right. So what I'm going to do with this, I cancel 2. Cancel everything out. Oof. It works very well in the morning's class, always. Computer. I should restart the computer before I come. Okay. So I'm going to cancel this 2. So I get 4 minus x squared to the 1/2 minus x squared 4 minus x squared to the negative 1/2. The question is how do I solve this equation? I set this to be 0. Well, just move this term here, right? Multiply both sides by same term to the 1/2. You multiply both sides by 4 minus x squared to the positive 1/2. So this side is 4 minus x squared. Then minus x squared plus 1. It's going to be 0. So x squared is going to be 2. So x is going to be plus minus square root 2. That's pretty reasonable, right? How do you see that? It should be plus minus. That's 2 numbers. Okay. Okay, when x is equal plus minus 2, the y value is a plus minus, right? Y value, let's look at the y value. When x equals positive square root 2, the y value is going to be square root 2, 4 minus square root 2 square, and 1/2. It's going to be square root 2. And here is also square root 2. That's 2. So when x equals negative square root 2, y is going to be negative square root 2. 4 minus negative square root 2 square and to the 1/2, it's going to be, so it's going to be plus minus 2. All right, so you get the absolute maximum value, absolute minimum value, sketch the graph. Okay. Now, so you get the right maximum value, minimum value, and where it is, right? One thing you probably have to verify this is, I know the second derivative should be somewhere positive. First the derivative, right? You look at the picture. I think, let me rewrite this picture, this function. F prime x, 4 minus x squared to the 1/2 minus x 4 minus x squared. Here, square, right? Negative 1/2. I take 4 minus x squared to negative 5 out. 4 minus x squared minus x squared. And you take 2 out. Okay. So you can tell when it's positive, when it's negative. Okay. Yeah. So again, this is going to be positive if x squared is less than 2. Okay. This is the same as x less than negative square root 2 or x greater than square root 2. The derivative is negative if x squared is greater than, hold on. Yeah, negative, that's a positive case. Yeah, positive case is different. Yeah. This is be x less than negative square root 2 or x greater than square root 2. So you can see where it's increasing, where it's decreasing. Inside the interval from negative square root 2 to positive square root 2, it's increasing. So from here, you can see that from this is negative square root 2, that's positive square root 2, and that piece is always increasing. Okay. When x is between negative square root and positive square root. So we got the graph, okay? And then you look at second derivative, and one side will be positive, the other side is negative. You can also check the second derivative. It's a little bit complicated, right? But I'm pretty sure this is going to be as a sign. You see, when x is negative, y double prime should be positive. When x is positive, y double prime is negative. I'm going to finish the computation. Okay, it's going to be the first one. That will be negative 4 minus x squared, negative 3/2, and I get negative 2x. And plus 4 minus x squared, negative 1/2, negative 2x. Okay. All right. So now we have to take things out. Okay. So you take. This is a little bit complicated. I take this out. Okay. I also take this out. Okay. I take 4 minus x squared, negative 3/2, negative 2x. Then I get this part only. Then I get 4 minus x squared. Okay. So I'm going to get negative. So I have 8 minus 2 will be 6. Positive x squared minus 2 is negative x squared. Right. But this one, this part is always positive. This part is always positive. So this determines the sign. It will be the sign of the second derivative determines the sign of x. So that's why this is going to be positive if x is negative, negative if x is positive. Okay, so when it's negative, concave down, when it's positive, concave up. And that matches what we discovered. All right, that matches what we discovered. So look at the picture here. When x is negative, concave up. When x is positive, concave it up. Okay, that's one point of infraction here. I did not have time to discuss number 9. My solution we posted online. Okay, and we will continue next class. Like whenever you have a question, you don't know how to do the problems, bring to the classroom.